Alright, we're back with Corona Calculus Part 4. I guess the title already gives it away, but today we'll be talking about the derivative. Oh boy. And as you might notice, I am reusing paper because you gotta save the trees. Anyways, don't mind that too much, hopefully. So from Part 3 at the end, we were doing some pretty cool slope things. Pretty cool, no? But let's try that again with, like, say, a more complicated function. So, another example. Say we have a function g of x equals to 2x cubed minus 3x squared plus 5x minus 1. And many of you smartos out there might just be like, oh, just bring down the exponent and then you'll be fine. Well, we're going to be doing this with limits because we're cool like that. So limit as delta x approaches 0. We're going to find the slope of this function at a certain point. So remember, slope equals to delta y over delta x, and as your interval gets, oh, I should probably draw a picture, crap. Okay, so we have like a curve here, and we have like a point here, right? Your interval x, and then your delta y, right? So this is your delta x, and this is your delta y. So as your delta x gets smaller and smaller, your slope approximation will get better and better. I hope you can see that. So for here, we're going to have delta x on the bottom because that's how slope works, right? And it's going to be g of delta x plus x minus g of x. I don't know why it's so many spaces, but I was going to write something else. But anyways, this equals to limit of delta x approaches 0. Oh my goodness. It's going to be quite bashy, guys. Okay, so I'm not going to write out everything, but it's going to be 2 delta x cubed minus 6 delta x squared x plus 6 delta x squared and plus 2x squared cubed. That's just the first term of g of delta x plus x. And then the next term is going to be minus 3 delta x squared minus 6 delta x minus 3x squared. We're going to do another line here, and this is going to be plus 5 delta x, and then a plus 5x, and then a minus 1. Alright, so that's the first term. Minus g of x, which is just 2x cubed minus 3x squared plus 5x minus 1. That's nice. And this is going to be all over delta x. See, that's why I need such a big line there. Anyways, we can cancel out some things, hopefully. So, if we, let's see what we can cancel out here. We can cancel out these, right? 3x squared, the minus 1, the 5x, and then the 2x cubed. Alright, and then if we see that the rest all have delta x's in them, right? 2 delta x cubed, we have 5 delta x, so 6 delta x squared times x. So we can just divide this delta x into the whole remaining thing. So this should equal to the limit as delta x approaches 0. Well, this one will be delta x squared minus 6 delta x plus 6x squared and minus 3 delta x minus 6x plus 5, and that's it. There we go. And then as delta x approaches 0, this will become 0, this will become 0, and this will become 0. So we're left with, well, we can evaluate the limit, and it becomes 6x squared minus 6x plus 5. Wow. Don't know where this could be going. Absolutely not. But that's pretty cool. We see that the slope of a cubic function is quadratic, depending on x. Pretty cool, no? Alright, that's it for examples. We'll cut to the good stuff. So, we found in general that for the slope of a function, f of x equals to the limit as delta x approaches 0 of f of delta x plus x minus f of x all over delta x. However, we could have also done the limit as x approaches a constant c of f of c, wait, shoot, right, f of x minus f of c over x minus c. Well, these aren't exactly equivalent, alright, they're not always exactly equivalent, I don't think so, but this is just another way to express the slope, right? Because as your x gets closer and closer and closer to c, your y value should also get closer, and then you can approximate your slope like that. This is like what you would do in like algebra 1 or something, where you subtract the y's and you subtract the x's, and then you get your slope. So when you're evaluating slope or trying to find the limits of certain slopes, right? Or sorry, you're trying to find slopes using the limit. Make sure you consider both of these possibilities, because one of them might be easier than the other to prove, or solve for at least. Okay, now we have calculus time. Whoa. So we're going to have the derivative is going to be our name for the slope of a tangent line to a function. Many of you guys probably already knew that, but it's cool. Okay, let's define this. Slope of tangent line to a function at a point. Okay. So as we already said, I already wrote out the two ways you could express the derivative. This is one way, and this is the other. Some more definitions. When you call a function is differentiable means, well, it's able to be differentiated. Alright, I guess that's self-explanatory. Now we have some notation. Okay. So for our notation, we're gonna say that dx of some function equals to do a derivative on variable x. So it's like with respect to x. Alright? So if you're like dy dx is it's like putting this y into here, right? So dy dx is just the derivative of y with respect to x, or the slope of the function with respect to x. Okay? Where y equals to f of x, I guess. Y must be a function that has an x in it, right? There is also another way to notate derivatives, where you can be like dy dx of f of x simply equals to f prime of x. Now, this is better in a way because it's way easier to write. You just stick on a little apostrophe. However, it's a little bit more confusing because you don't know if you're doing the derivative with respect to x or some other variable. But right now we're only doing single variable derivatives, so it should be pretty clear that when we write f prime of x, we're going to be doing derivatives with respect to x. And for this Corona calculus series, we'll be just using f prime of x most of the time. Okay. And lastly, we have some continuity importance. So here's a theorem. If f is differentiable, that implies that f is continuous. Oh, sorry, this is all on a point C, at C. Okay. I guess we can prove this. It's proof. Hopefully I still remember to do this. So f differentiable at C means there exists a k such that the limit as x approaches c of f of x minus f of c over x minus c equals to k. Notice we're using the x approaching c method of finding a derivative instead of the delta x approaching 0 because we want to include a c in here, right? We're using this definition because we want to express x and c in a single limit. So we want to show our then part, our f is continuous part, means we want to show that limit as x approaches c of f of x equals to f of c, right? That's what continuous means. Notice how this is a constant, right? So let's see what we can do here. Let us my notes are pretty crappy. So for this to exist, I think, I think it's an if and only if. I think that's how it works. Yeah, it's not just one direction; it's both directions. That should make more sense. Well, crap. We're gonna do this direction first. We're gonna assume that this exists. All right. If this exists, then that means the limit. This equals to the limit as x approaches c of x minus c over x minus c, right? This is just the value of 1 times f of x minus f of c. Wait, no, shit. Alright, it's just me struggling now. Oh, I see. We know that the limit as x approaches c of f of x minus f of c equals to so this, if this exists, alright, this equals to the limit of as x approaches c of x minus c over x minus c times f of x minus f of c. Alright, just bear with me a little bit. Oh, jeez. And then we can bring this x minus c under, so this equals to the limit as x approaches c of x minus c times f of x minus f of c over x minus c, right? this equals to the limit as x approaches c of x minus c times the limit as x approaches c of f of x minus f of c over x minus c. So we know that if this exists, then this exists, because this is a constant, right? Honestly, I probably didn't do this correctly, but you should probably Google differentiability implying continuity, because that's probably pretty important. And I think I bungled up this proof, but maybe you guys can do a better job. Alright, that's it for today. That's the derivative.